All attendees are in listen-only mode.
Hey, good morning from a little bit foggy Santa Barbara, California. My name is Stefan Kemmer with Bruker Nano Surfaces, and I welcome you to our webinar, AFM meets Raman spectroscopy. So we start with, because that's a webinar that's a little bit different than our regular AFM webinar, so we might have audience from the Raman and from the AFM side. So I'm going to go just extremely briefly through how does actually an AFM work and what is the Raman effect, so just so that we are all on about the same page. We will then go through some co-localized measurements where we combine conventional AFM and conventional Raman spectroscopy together and analyze a sample, the same area on the sample, and see what we can learn with it, see what kind of options we actually have to do these kind of measurements. And we will then at the end talk about what we can do when we actually take advantage that we have an AFM tip which is significantly sharper than the focus spot we can achieve with the conventional optics. That will lead us to the subject of TERS, tip-enhanced Raman spectroscopy, and then we will conclude with a one short slide, and then we will have a question and answer session. I would also like to kindly ask you at the end of the webinar, before you leave it, there's an extremely short survey. Please fill it out because, again, it helps us to tailor the webinar series to your needs. So if there are any subjects that you would like to us to present, talk about, I mean, please mention it, because if you don't mention it, we just don't know it, and then we just talk about whatever we like to talk about, so which might or might not be interesting to you. So why do we actually want to combine AFM and Raman? Well, we want to combine AFM with more than Raman. We want to combine AFM with spectroscopy. And the reason is very simple. I mean, you have nanometer-sized resolution in an AFM, and you have sub-micron-sized to micron-sized or even worse resolution in other spectroscopies. However, you get mostly chemical information from other spectroscopies, so it's a great way to combine these technologies, because potentially you get a beneficial information out of both that would help you either be more productive or just learn more about your samples. But before we can go into a little bit more detail on that, let's just quickly look at how an AFM works. An AFM in general has a sharp probe that is attached to a cantilever. They're micro machined. They're typically made out of silicon, and you bring that cantilever tip assembly into close proximity. That could be contact, could be very close to the surface of a sample. Then you move it around in X, Y, and Z, and you can move either the sample or the tip. It doesn't really matter in terms of understand how that AFM works. And then you measure some kind of interaction, and that interaction simply causes, if you tailor the tip right, causes a deflection of that cantilever, and there are many means of measuring the deflection of the cantilever. And one of the very common ones is what's called a beam deflection. So you simply shine a laser spot onto the cantilever. It's reflected off into a photodetector, and you monitor that movement on the photodetector, which in turn is proportional to the movement of the cantilever. So when you look at it a little bit more detail on the right side, you can do what's called a force distance curve. What you simply do here is you take your cantilever tip assembly somewhere from far away, which is indicated on the red line on the right side. So your cantilever is like a micron or higher above the sample, doesn't feel any interaction from the surface. So when you move now the cantilever tip assembly closer, nothing will happen to the cantilever. It will just stay straight. At one point, the force between the tip and the sample becomes so big that it overcomes basically the force that is determined by the spring of the cantilever. The tip snaps to the surface, and from that point on, when you push your tip further into the surface, the cantilever will just deflect. That deflection can give you useful information about mechanical surface properties and so forth. And we can extract that in some of our AFM modes. Then you can take that whole thing and pull it back. And usually when you pull back, as indicated on the blue line, when you come to point number 4, you can actually pull back further than what it actually took to snap the cantilever onto the surface. That is caused by adhesion surfaces, forces on the surface, and then the cantilever at one point pops off because these forces become too big for the, again, force that the cantilever can hold, and you come back to the original starting point. That thing, again, is called a force distance curve, and it's an extremely useful tool in scanning probe microscopy, as it gives you information about mechanical properties, compliance on your sample. It can give you information about adhesion on your sample. It's useful to examine at what working point your feedback will work and so forth. So now what we have done lately is we take this force distance curve and we execute it in extremely fast succession, creating a kind of what almost looks like a heartbeat when you go to the doctor's office, as shown on the right side. I mean, you could use that pattern basically to scan our surface now. The predominant mode in the past was tapping mode, but we found that mode, which we refer to as peak force tapping, a much more useful mode because it has a lot of advantages that allow us to extract, in addition to topographic, also a lot of quantitative information out of the surface. To make it short, at the end, you get quite high resolution images with an AFM. At the bottom, you see 2 images of an alkane. So these are alkanes, the long worm-like structures. There are individual alkane molecules that are deposited on graphite. The left image is taken where the sample was at room temperature, and then we heated the sample up to 70 degrees C, and you can see that there's some better ordering at 70 degrees C, so the molecules become a little bit more mobile to arrange themselves better to the underlying structure of the graphite surface. So that's what AFMs can do. If we tailor the tip to a specific interaction, we can measure all kinds of quantities. So we can, of course, measure topography. We can measure electric, magnetic, thermal properties, and I already mentioned we can measure nanomechanical properties. In talking in optical terms, a field of view is typically a few nanometers up to 100, 200 micrometers in XY, and typically 10 to 20 micrometers in Z. Lateral resolution is around 1 nanometer or so. The vertical resolution is sub-nanometer, and the imaging time is seconds to minutes. On the right side, I'm going to just show you a quick video of how fast AFMs can scan these days. So that's an image of a biodegradable polymer that was imaged at 100 Hertz scan rate. It's a 2 micrometer field of view here. So each frame that you're going to see took about 2.5 seconds. And what you see here is that the polymer actually changes its state, and you can see these crystalline domains growing towards each other. You can observe the kinetics and so forth with these high-speed AFM data. So we have high resolution with an AFM. We are fast with an AFM, but and we can measure a bunch of quantities, but we still measure chemical specificity, and that's where, of course, spectroscopies come in, and Raman being one of them. So now, what is a Raman spectroscopy? So it's an inelastic collision as compared to infrared spectroscopy. So we have light here indicated in the top diagram, with the green arrows coming in from the left. It collides with the molecule. If the molecule changes polarizability, that means it is Raman active, and some of the light that is backscattered will be shifted in color. Light can be either blue shifted or red shifted, leading to Stokes or anti-Stokes Raman scattering. Most of the light is not shifted at all. It's just scattered, leading to what's called rare light scattering. And that's one of the problems in Raman, is that the Raman cross-section, or the chance of an interaction, is actually quite small. So the signals that you get in Raman spectroscopy are quite small. So what do we need in order to get to measure a Raman spectrum? In the very simple terms, I have a diagram here on the top. Typically, a laser is taken these days that illuminates a sample. You then have a filter that basically cuts out most of the incident laser light and leaves only the light that is shifted in the beam path. You then disperse the light with a grating and focus it onto a charge-coupled device, which then generates a spectrum. There are two spectra shown here on the bottom. One is polystyrene, one is PMMA, and you can see that there are very specific peaks, which are specific to certain groups in these molecules that show up here, and you can plug in these. For example, one thing you can do is you can plug in the spectra into a library and then hopefully get an idea of what is on your sample. But you can do more with the Raman spectrum by looking at the shape of a peak, the width, and so forth. I mean, you can get information, not only information about composition, you can also get information about crystal symmetry or orientation, because polarization of the beam can give you useful information here. You can learn about stress and strain in a sample. You can learn about the quality of a crystal to an extent, and you can get some information about the amount of material on your sample. So it's quite complementary to AFM actually, which really makes it a nice fit, and it becomes even nicer when you look at the resolution and imaging time. So resolution, it's an optical technique, so it's restricted to diffraction. So lateral resolution is 250 nanometers at best, vertical resolution 500 nanometers or so. Of course, if you use objectives with a little bit, not the highest NA possible, I mean, then these numbers will go down, I mean, or will go up, so the resolution won't be as good. Imaging time, seconds to minutes, so very much comparable to AFM here. Again, just reiterating the point that it's a quite nice fit. So when you want to do co-localized measurements, you basically have two choices. Choice number one is you can build a combined instrument. And I have a couple of examples here. On the left side is a very nice integrated system, the Bruker NEOS AFM together with the Bruker SENTERRA. And we didn't show the enclosure, the light-tight enclosure around this instrument here, just to show you the instrument. So the AFM is basically built into an objective of the microscope here, and the Raman microscope, the SENTERRA sits on top. You can combine with, and it's interesting to see it in quite slightly different ways. We can combine, for example, an icon, the Bruker icon AFM, which is shown on the top here with a GY lab RAM spectrometer. And what you see on these two images here is on the left side you see the sample in the AFM analyzing position, and then we can move the sample over, and you see like the red Raman beam here on for educational purposes. That will be the position to do a Raman measurement. So again, a nice combination, combining a top-of-the-line AFM here with the Raman spectroscopy. So the two examples I just showed you right now were both in reflective configuration. You can of course also do Raman in a transmissive configuration, and one example here shown at the bottom is the Bruker Catalyst AFM, which is most used for biological application. But I mean, nobody prevents you from doing material science studied with it if your sample is transparent, combined with the Renishaw in via microscope. So when you do these combinations, of course it's sexy to have a combined instrument, but you have to keep in mind that when you combine two instruments, that's a general statement, you have to make sure that both instruments after the combination still function close to its original specs. Meaning in a Raman microscope, you often have a lot of high-powered lasers which might be close by. So you might have to move these lasers to a different table to avoid vibrations. AFMs are very susceptible to vibrations, which somebody that does pure Raman spectroscopy might not even think about. And vice versa, there are AFM things which might affect the Raman microscope. So when you look into these co-localized solutions, you want to make sure that you just don't take two pieces and slap them together, but that it's done properly and that the specification of both instruments are still there. There's of course another approach that I have not shown here that allows you to do these co-localized measurements, and that's maybe not as sexy, but it's actually quite nice because it completely leaves the instruments intact, and that is a shuttle stage. So if you take a stage which has an index sample mount, you can actually take that stage and move it around between AFM, between Raman. You can even put it on an IR spectrometer or other analytical instruments attached to a microscope to do studies on the same sample area. And the big advantage is all these instruments are completely unmodified. So it's quite straightforward to have them operate at their specs here. Let me show you one example here, and that is a study on yttrium-stabilized tetragonal zirconia polycrystals, and that's a material that is used as an example in the dental field for dental implant ceramics. It's also used in a lambda sensor in your catalytic converter in a gas engine. So what's the problem that we try, or why do we actually want to study that material? So that material is typically sintered, and it contains its tetragonal crystalline structure. But if something happens with the internal pressure, you can have a transition from into the monoclinic phase, and that's an unwanted phase. And so the trick is to figure out, did this transition happen, yes or no, and then where did it happen on my sample? Once you learn that, I mean, you can try to mitigate the issue or avoid the issue in the first place. The instrument we use to study this subject here is the NEOS-SENTERRA. We use the following modes on these instruments here. On the optical microscopy side, we use bright dark field and a differential interference contrast, basically to navigate around on the sample, find an area of interest where we want to perform our AFM and Raman study. And then we use the AFM to get a 3D surface image, quantify some of this information on the surface, such as roughness and grain structure and size. And then we use the Raman microscope here to identify our crystallographic phases and localize them. So we basically have the whole process between navigation and analysis here nicely built into this one system. So when we take a Raman spectra shown in green here of our sample, we see a number of peaks. Without going into great detail here on the specific peaks, when you take a spectrum of only the tetragonal phase shown in red, you can clearly see a difference, and that is there are additional peaks present in our sample here, which indicate another phase on our sample. So that basically helps starting out the study here. And the sample is courtesy of Dr. Hallmann, the Center of Dental Medicine in University of Zurich. So now, what you can do is, if you have two spectra, you can subtract them. From each other, and that is done here. So the blue spectrum is the subtracted one from the two in the previous slide. And when you then compare the subtracted spectrum to a reference database, you actually get a hint that this is indeed a monoclinic phase that is shown up in the spectrum here. So now we do know that we have monoclinic areas in our sample. The question now is just, where are these areas, and are they related in any way to any surface topography information that we might be able to identify with the AFM? So we can do optical spectroscopy on the sample. Start on the top left. That's a simple bright field image. You see the sample is inhomogeneous, just judging from the contrast in the optical image. In the DIC image, we can see some surface roughness, and when we zoom in a little bit, we can see that even a little bit clearer, as shown in the green images. On the bottom, we can see some cracks, we can see some particles, and on the bright green image in the with the DIC with the interference contrast, I mean, you can clearly see there's some rough area coming in from the left here, almost looking like a triangle, some smooth area and some rough area surrounding that part. We can now take that DIC image to use that as a navigation for our AFM. Shown on the left side is the DIC image it's in green, 80 by 80 micrometers, and the white square denotes the area that we are now scanning with our AFM. It's a 40 by 40 micron scan. Has Z variations about a little bit less than 3/4 of a micron. And we can now even more clearly see the smooth area at the bottom and the rough area on the top. We see some holes and a few cracks. But now comes the beauty of AFM, because we have full three-dimensional information of our sample. We can actually quantify these areas, and that's indicated by these little boxes here. So inside each of these boxes, we had our software measure the standard conventional roughness information, as indicated by the columns here, SA for average and SQ for RMS roughness. And you can see that when you look at the boxes in the smooth area, so 1 to 5, I mean, you get a average roughness of a little bit less than 9 nanometers, and you get a significantly higher roughness in the what we call the rough areas of about 60 nanometers. So not only can we look at these areas and say, yeah, that looks rougher than the other one. No, we can actually quantify this information now. We can zoom even a little bit in further here. We can look at the grainy structure on one of these smooth areas, and then we can measure the grain size. Again, that's now beyond what you can do basically with most optical microscopies here. We can go even further. We can look at the fine structure on some of these grains, as shown in the slide here. So we start on the top left with our original 10 by 10 micrometer image, and then we zoom into about a 3 by 3, and we can see, and we see that on the top for the smooth and at the bottom for the rough areas, and we can also see that the grains look completely different. I mean, on a larger scale, they were just grains, but now we can actually see that they look like flat on the smooth areas, where they seem to exhibit some distinct facets on the rough area of the sample. Now that we have gathered some information with the AFM, now we can actually bring turn our Raman objective with the turret, turn the AFM objective out, turn the Raman objective in, and And now we can do a Raman analysis, and what's done here is basically you position a grid of points that you would like to analyze over your sample, and then your system would take a Raman spectrum at each of these points under predefined conditions, and then what you get is shown at the bottom here. That's the extraction of two spectra of these areas, indicated on the left by the red and the black arrow in the optical image, and then further on the right indicated on the in the AFM image. And you can clearly see that that on the smooth areas shown on the bottom and shown as a black spectrum here, you do not see the monoclinic phase present, and on the rough area you do see the monoclinic phase present. Once you've finished one of these Raman maps, you can of course take a single spectral region here and basically integrate over that region, and that is shown at the bottom here. So here only a small area from 180 to 184 wave numbers is used for integration. And then you can actually see that this area basically, where this area shows up in blue here, and the monoclinic area shows up in red. And you can again correlate that very nicely with the AFM images. So quite a nice application here. Again, we can have we have our if you go back to our original mode that I showed you on the instrument. So in the dark field, you can pick basically up an appropriate area for the AFM scan. You see the overall shape of the sample. You get, of course, enhanced surface contrast the moment you kick in the differential interference option. And the AFM lets you quantify surface morphology in this case, and the Raman then lets you identify and localize the crystalline, the areas where the phase transition occurred. So quite a nice study, and of course there are more of them. It's just not enough time in one short webinar. So what I want to spend the rest of the time is basically showing you what we can do when we actually use the AFM to enhance the optical signal here. And the generalized setup here, which I took from Marcos Raschke's website at the University of Colorado, is shown on the left side. So you have a sharp tip, sharp meaning somewhere between like 1, 2, and maybe 20 nanometers or so, and you illuminate it with light, and then the tip somehow enhances the optical field that is present, and some light is scattered back, and you can collect a variety of information here. You can collect the Raman effect indicated by Raman scattered light, indicated by omega plus delta. You can scatter linear scattered, and you can do some second harmonic generation. It's completely up to you what kind of detection scheme you place after that tip here. Now maybe step back. Why do we actually want to enhance the signal here? Why don't we just take a tip, shine light at it, and look at a small area without any enhancement? The problem is that I mentioned originally that the Raman cross section is pretty small, so the signal is already small to start with. And when you suddenly go from let's say micron-sized spot to a nanometer-sized spot, you simply would not end up with enough signal to get actually anything useful onto your detector. So there is a need to enhance the, in this case here, the Raman signal to get actually something useful onto your detector. So now how can you set up an experiment like that? And basically you have three possibilities. Number A is maybe the most obvious, that is the transmissive configuration, where you have your tip coming from the top, you have your sample, and you illuminate the tip from the bottom. That of course requires a transparent sample. Advantage is you can use high numerical aperture objectives to maximize the light collection here. Most samples, however, that we deal with are not transparent, they are opaque. And here we have possibility for B and C. B is a side-on illumination here, where we illuminate the tip from the top at an angle. Straightforward. Disadvantage is, of course, that you can't use an objective with an NA as high as you use it in transmission mode. To overcome that, a few groups use a parabolic mirror approach, as shown at the bottom, a numerical aperture 1, basically, because everything is in focus. But experimentally, not that easy to set up, because small angular changes of your mirror will, of course, cause issues with the focus instantaneously. So, the few examples I will show you are obtained in configuration B here. Just briefly, so if you want to read up a little bit more on TERS, I have some, of course, completely arbitrary selected by me papers here on the right side, but they might be a good starting point. Also, Renato Zenobi just has a great review overview paper out there that is a good start to get into the field and read a little bit up more. So when you simulate, and there are a bunch of simulations out there on that field, I just picked again one here. There are a couple of things you have to do is when you illuminate a tip, you have to make sure the tip will act as an antenna. So you have to make sure. So you have to use a metallic tip, and the typical metals used are coinage metals, so copper, gold, and silver. And which metal to use depends basically on the wavelength that you would like to use for illumination, and then also on the shape of the tip. So for these typical sharp AFM or edged wire tips, silver and gold are used. Silver mostly for green illuminations of 532 or something like that, and gold for 633. With silver having the additional advantage of giving a slightly higher signal enhancement, of having the disadvantage of being silver, meaning that it degrades quite quickly, oxidizes from sulfur, or it's not exactly clear what happens in a quick time on a silver tip, but it degrades. It is clear that it degrades quite quickly, whereas gold is way more stable. So when you illuminate the tip, you have to make sure you want to at the tip have the tip act as an antenna, and you want to excite a plasmon resonance. So you basically have the free electron gas in the tip, and you want to excite that. So you have to hit that with the proper with your beam in the proper orientation. So the polarization of your incoming beam is quite important, and you want to have it so that the beam is polarized vertical to the tip axis. When you do that, I mean, as shown on the right side here, Ki, your tip cannon forms. I mean, you have a plasmon resonance, so your tip acts as an antenna to enhance the incoming field, but it also acts as a transmitter to enhance the outgoing field. And that's why typical these enhancements, when you often see like e to the power of 4, that is because you have two enhancements going on. You have an incoming field enhancement and an outgoing field enhancement. That's where the factor e to the power of 4 comes in. And what you see on the right here is when you use a substrate now, where you can also induce a dipole, as it's shown on the tip here, then you can actually even get a higher enhancement. So let's say use a gold tip. If you also use a gold substrate, you end up with what's referred to as gap mode imaging. Then you can actually get a much higher enhancement, because you also have basically you induce a dipole into the sample, and then you get a much higher field. And you can see that here in the simulation. I mean, when you just look at a single tip, you have an enhanced field here of an arbitrary factor of 20. And when you bring in a metal substrate, then suddenly you have a field enhancement of 180 here. So that's why you often see in the literature that people use like a metallic substrate when they perform the TERS measurements, even though it's not necessary, but it definitely helps with the enhancement here. And the enhancement, of course, is very localized to the tip, and hence this is the trick how we beat the diffraction limit here. Our spot that we focus on the sample is, of course, still diffraction limited. Size depends, of course, on the orientation of our optics and on the numerical aperture of the objective, but the field, the strong field, is only in the vicinity of the tip, and that gives us the high resolution. It also has a different effect, and that is it decays very quickly with depth. So when we when we compare conventional Raman with TERS, one of the immediate effects is that in TERS you are sensitive to the surface. You almost have no depth information coming from the sample, so you're really probing a very small layer of material under the tip. So what angle, if you want to look at the reflective configuration here, like a diagram is on the right side, we have our tip here. And then often you see angles. So what's referred to as the angle here is basically the angle of normal that we want to put an objective in. And it turns out that about 55 degrees or so is optimum if you use your tip for illumination and collection. And that has also to do with the fact that you want to illuminate your tip, and then you get a signal, a backscattered signal, and the signal that you get back has basically two lobes which sit underneath the tip. And when you look at the geometry of these lobes, I mean, it turns out that 55 degree an objective at that orientation is about the optimum to do a TERS experiment in reflective mode here. One thing that is seems to often cause some confusion is like when you read about these enhancement factors in the literature. And again, a great explanation here is given in the paper that I've cited here at the bottom from Thomas Schmidt and Renato Zenobis group. You see these contrast factors, and what you always have to watch out for is how do people actually measure the enhancement that they state. And that's why I have the formula here. Basically, the simplest way is to define something like contrast. You basically have an intensity with tip, and you have intensity without tip, and you divide these two, and you get a contrast factor. And it's typically like, what have you, like between 5, 25, 30, somewhere in that range. Because the physical meaning of that is there's really no physical meaning to it, because you do not take into account any geometrical effects. However, for practical reasons, it's extremely useful, because I mean, you see a spectrum where your tip is not in the picture, and then you get a spectrum where your tip is there and enhances the field, and contrast is basically the difference between these two. So it's an extremely useful direct measure for what's actually going on here. Now, if you want to go a little bit into enhancement, what's the actual enhancement factor, then you have to take into account either the differences in area, so between the far field focus and the area underneath the tip, or you have to take into account the volume, right? So, and again, watch out when you see field enhancement numbers. I mean, how were they defined, and how did people, for example, verify that the tip was really only 10 nanometers or 2 nanometers or 20 nanometers? So again, because of the uncertainty, contrast is a very nice way of stating it. Even though the numbers don't look as impressive, it's completely clear what's actually meant here. So how would a commercial instrument look like that does TERS in reflection mode? And one of the examples I've shown here. What we see on the left side is the Bruker Innova SPM. What we see on the right side is a Renishaw in via Raman microscope. And what we have here in between is an optical arm that illuminates the sample at the appropriate angle, collects the light back into the Raman spectrometer. What of course not shown here is the software that makes sure that these two instruments work properly to each other and allow you to do the correlation. So we have a hardware integration and we have a software integration. The hardware integration allows you to, and I mentioned that originally, both instruments individually without any compromise in performance. And that's, again, that's a point that I cannot stress enough. It's you might think, when you come from the Raman side, you might think, oh, the AFM, it's just a tip that is a need for me to place somewhere on the sample. And that is in some way correct. However, you have to make sure that the tip is placed accurately on an area of the sample, that the tip stays in that area, and that the tip does not make any unwanted movements. And that actually requires a good AFM. So it's not just enough to take two plates and drill a hole into it and glue some piezo's underneath and claim, oh, I have great optical axes, but you have a not so good AFM. That doesn't really help you in this case here. You want an extremely stable AFM for these type of measurements. That's one of the reasons why we choose the Innova for that kind of setup here. So you have a hardware integration, and then of course you have a software integration, and that software integration allows you allows these two instruments to talk to each other, and then also create Raman maps by basically positioning the AFM tip over various areas of your sample and automatically collecting maps and so forth. It also allows you to do approach curves, which are quite an important measure to figure out if you are really doing a proper near-field microscopy here. So we look a little bit on how the view when you operate one of these instruments, what would you actually see? So on the top, you see an AFM tip illuminated by the Raman excitation laser. Here you see a little red spot in front of the tip, and that same tip, as viewed by the Raman objective, is shown on the bottom right. Right, you have to. The tip looks at an angle here, so it maybe not a view that you are immediately used to, but you can clearly see the tip here. You can see the red Raman laser illuminating the tip. The white scatter that you see around here is the IR feedback laser used on the AFM. There's a filter that you can place in the camera, but we removed it here for experimental purposes. Okay, so then what do you get when you take a tip and bring it onto a sample? And what we did here is we looked at a quite simple sample. It's a dye. What you see on the right side is the gold tip, the Raman laser illuminating the tip, and what you see on the left side is the Raman spectra taken at various distances. So what we do is what we call an approach curve, and it's very similar to the force distance curve that you showed you in the beginning. So we basically take our tip and slowly move it towards the sample until we are at a stable distance in feedback at the sample, and then we can move the tip back and forth, and we can measure spectra at various distances. And you can see here that the spectra is clearly enhanced. There is clearly a spectra in feedback, as shown by the green spectrum. And then if you go only 50 nanometers away, there was actually a spectrum at 20. I don't know why it seemed to have gotten lost. And then at 50, at 100 nanometers, the spectra is basically not enhanced anymore. And you can clearly see there is a near-field effect. So our tip is really enhancing the spectrum, meaning everything is working. We're using the right polarization. We are collecting right, and our instrument is nice and stable. You can do the same thing with an AFM tip. Because with AFM tips, the bigger problem up to this point is that when people use wires, it's a solid metal, and the procedures for etching these wires are well defined. When you use an AFM tip, for the most part, people coat these AFM tips with metals, and that is often not as the coating is not as stable as a solid metal tip, meaning you have to use significantly less power. And but in any case, what's shown here is we can do that because we can scan our sample here, 2 micron scan in tapping mode, and then we can take a spectra with the tip in feedback and with the tip retracted. And again, we see some enhancement and would be ready to do TERS experiments now. You note that the power used on the AFM tip was significantly less than with the STM tip, because what you want to avoid is destroying the coating that is on the tip in this case. Now, data out the literature here from Raschke's group on the left side and from the Nobis group on the right side. You can do that. So when you talk about resolution, there's two types, right? There's spatial resolution, and these numbers right now go between 2 nanometers and somewhere less than 20 nanometers, somewhere in that range. It depends a little bit how you define resolution, but it's definitely somewhere in the area of the tip radius, or even better than the tip radius. And then there's also how much material do I actually need to get a useful spectrum, and single molecule sensitivity has been demonstrated by these two groups, as shown by Raschke on Malachite Green. And these are both experiments in reflection mode, and by the Nobis group on BCB here. And again, in both modes, AFM was shown, and the STM mode was shown here. So it's a great technique. It certainly needs more research before it becomes something that an industrial customer would use. But it's an interesting field to do research in. Things look different in the near field, and it definitely gives you a lot of research areas to work with. So if we conclude up to this point, I think we've seen that AFM and Raman spectroscopy are just perfectly complementary techniques. When you do co-located measurements, you can carry them out with an integrated solution, or you could use a shuttle stage. The advantage of doing co-localization is the interpretation of the respective data is straightforward. I mean, you're not doing anything to the Raman side, you're not doing anything to the AFM side. So the interpretation is whatever you're used to, coming either from Raman or the AFM or both sides. TERS, of course, catapults the Raman resolution to the AFM level, and opens a new field for research. There's plenty of stuff available, and it's quite an exciting field, to work in. So if you would like to contact me directly, I mean, I have my email address here, our website where you can find our webinars, and also an announcement, and also recorded webinars is shown here. And if you would like to contact one of our friendly sales guys, the information for product info is shown here. And if I manage now to open my speaker panel here, then I'm able to answer some questions. Okay, hold on here. What are the advantages of the Innova AFM versus the Icon AFM? What are the advantages? In what terms? So there are different AFMs. So the Icon AFM is a tip scanning. So I just gave a brief explanation to AFM. So in AFM, you can either scan the tip. So you have to make a relative movement between the tip and the sample, right, to get your field of view, to get your image. And you can either scan the tip or you can scan the sample. In the Icon instrument, you scan the tip. That basically means you can use a sample of almost any size. In the Innova AFM and in our multimode, we scan the sample. That restricts you in terms of the sample size. Right? So it's a different thing. When you do optical measurements where you rely on an optical beam be focused on a tip, one thing you don't want to do is you don't want to scan your tip. So in the TERS measurements, you basically can't do with an Icon instrument without significant demodification, because you're scanning the tip. So you would focus your laser beam on the tip, and the moment you start your AFM scan, you would move that tip through the beam, right? So you wouldn't get a TERS signal. In the Innova, you focus your laser beam on the tip, and then you scan the sample. So your tip constantly stays in the focus, and you have the enhancement. So different things here. The other thing is the icon costs about at least twice as much as the Innova here. It offers you also more possibilities. It offers you a fast scanning option and so forth that Innova doesn't. But if you're looking at an AFM suitable for TERS here, icon is maybe not the ideal choice. You want to go with an instrument that scans a sample, and that would be the Innova in this case here. Okay. Is it possible to obtain an AFM image and Raman mapping simultaneously? Yes, you should be able to do that. It depends on the instrument that you are using. And of course, when you do, like, let's for example on the Innova TERS combination that I showed you. I mean, any instrument that can do TERS, that is TERS enabled, is automatically co-located, right? Because if you're not co-located, you can't do TERS because your tip is not in the optical focus spot here. Can we use liquid samples to do optical measurements? Well, I assume you meant samples solids in liquids, not. I mean, you cannot scan, or it's almost impossible to scan a liquid with an AFM. I mean, you need some kind of solid sample typically. However, you can do experiments in fluids, yes. So that is possible. How do we take care of the vibration coming from the laser of Raman in TERS? I'm not exactly sure what you mean by the vibration here. If you mean power supply, fans or so, well, you try to move them as far away from the AFM. A lot of TERS measurements are carried out with red and with 530, so with a Heine laser and with 532 light. And I mean, a Heine laser doesn't really vibrate that much when you have a small power supply, but you can typically place that power supply under the table on the floor, and then it doesn't affect it. Of course, when you do, but not just in TERS, even when you do these combinations and you have a laser that has like a huge water cooler or so, and you have it basically sitting next to an AFM, that will affect your AFM performance. It's not a great idea to do that. So you have to take care of that. We would like to know if it's possible to carry out nanoscale imaging with these devices about smoothness and roughness. Yes, I think that's what I showed you in the example of the ceramic. Is a pulse laser required in TERS? Absolutely not. You use a continuous CV laser, so that's perfectly fine. What are the achievements of TERS in aqueous solution? I think I've seen there's a little bit of work, but not too much. I mean, it's not that easy, and I mean it just doesn't get easier when you add liquids. In general, when you work with a complicated technique, it's advisable to keep the conditions as simple as possible until you understand the technique completely, and then complicate the conditions. At least that's the way I try to approach things, and I think most people do. So, is TERS possible with icon? I think we went through that. If you would modify an icon by placing an XY or XYZ stage underneath, so to scan the sample, then you might be able to rig something up. But again, I mean, so it should be possible, but it's nothing that we at this point promote or sell. In what mode do you do the fast scanning AFM measurements? Contact tapping, or do you push the tip in and out of contact at each pixel? Well, in tapping mode, you do move the tip in and out of contact at each pixel, right? That's the definition of tapping mode. You just do it at resonance as compared to peak force tapping. But this mode was done. The fast scan image I showed you in the beginning on the crystallizing polymer was done in tapping mode. Are there tips which may have a Raman spectrum adding to the Raman spectrum of my sample. Where you see luminescence from tips, right? So when you use a gold tip, I mean, you can definitely see the luminescence of the gold. So yes, but you really don't see a spectrum. I mean, but you can get a spectrum from the tip quite quickly when, and that's why I mentioned your AFM has to be stable. If your AFM is not stable, so let's say you hold your tip a nanometer above the sample, right, to do a TERS measurement, and now you have an AFM that is not stable, that vibrates actually half a nanometer or even more. I mean, a nanometer. I mean, 2 nanometers. Then you would contact your sample quite hard at times. Or when you start scanning and your instrument is not fast enough in terms of reacting, you would smash your tip into sidewalls of objects. And then your tip would easily pick up, I mean, the tip could just damage very quickly and just not work at all. Or your tip could just pick up stuff from the sample. And then, of course, you would get a spectrum of whatever you picked up from the sample. Because you now have it at your tip, you would get a spectrum, permanent spectrum from that until you exchange the tip, basically. How do you ensure retracting of the tip exactly at 50 nanometer? Well, because we have a closed loop system in there. We have a sensor built into our systems. The best sensor we have right now has a noise level of 35 picometers. So quite low. So we have a sensor basically that measures where our tip is at all times, and that's how we know the distance in Z. So it's a thing that we understand quite well, and that is doable. Does the CCD require special characteristics for TERS? With those required for usual Raman? No, not really. I mean, you can use the standard stuff. I mean, from like Renishaw uses, they built their own cameras, and then most other people use the EM cameras from Andor. I mean, we have a liquid nitrogen cooled Princeton in house, which works fine. So I mean, that's all good. So whatever works basically for whatever. You need a cool CCD, but whatever cool CCD works for in a good Raman microscope will work for TERS. Is there a test system available in Germany? Yes, there should be at least a NEOS-SENTERRA, so a co-localized system available in Germany. And if you can just contact me or contact the product info webpage there, and then I can point you in the right direction. Just send me an email, then I can point you in the right direction here. Would it be easier to integrate the Raman technique with the icon as the large scanning stage was already fitted? I'm not 100% sure what you mean by that. Sorry. Can you combine the dimension icon with Raman? Yes, there's a co-localized setup that we have. There are actually 2 pictures of that setup in the presentation that I showed you. In a TERS experiment, is sample fluorescence also enhanced? Yeah, but it's also quenched, right? You have a metal tip, you quench fluorescence. I mean, fluorescence is never nice, but so you have similar issues that you have in conventional techniques. Similar, not exactly the same. Is it possible to obtain results from ppm concentration? Oh, well, yes, I showed you that in principle it's possible to with TERS to go to single molecule sensitivity. So, okay, excellent. So if you have any further questions, just feel free to send me an email. Otherwise, I thank you for attending, and have a nice day.